Hi there, welcome to this course on object-oriented concepts on Java. First, a disclaimer. This is not a course where you would learn the syntax of Java. So the focus in this course is not learning the syntax of Java. The focus of this course is on understanding the object-oriented concepts. So we want to discuss concepts like inheritance, polymorphism, encapsulation, coupling, cohesion, and look at them and try to get an understanding of them. That's basically the objective of this particular course. We want to understand object-oriented programming much more with examples. We end the discussion on object-oriented concepts by looking at some object-oriented principles, which are called solid principles. What are we waiting for? Let's get started. Let's start with inheritance. What is inheritance? Let's quickly define a couple of classes. Let's create a class dog. Let's say I would make the dog have a name. So let's have a dog with a name. In this particular series of examples, I won't really sometimes not create getters and setters, and I'll just keep it very simple so that it is easy for you to follow and look at it in the screen directly. So a lot of places I wouldn't make the variables private. Let's say ideally I have to make this private and I have to create a getter, setter, and all that kind of stuff. I'll stay away from it a little bit. Wherever it's needed, I would do that. But for most part, I would try and stay away from that and really focus on discussing the concepts. So the dog has a name. A dog has a name, Puppy, Julie, whatever you'd want to have. So let's say there is another animal. Let's say another animal class, cat. Now, the cat also has a name, maybe a different name, but it also has a name. So if you look at these two classes which are present right now, these two classes have something in common. That's a name. And also they belong to the same category. I can call both of these animals and every animal can have a name. In that kind of situation, what I can do is I can create something called an animal with a name. So the animal has a name now, and I can make the class dog extends animal. Thereby, you would see that even the dog would get a name. Let's see how that happens a little later. So now I can do class cat extends animal. Okay, that's great. So what we'll do now is let's create let's use a main method. So I'll quickly create a public static void main, which will enable us to run the programs whenever we need them. And I would create an instance of the class dog. Dog is equal to new dog. Aha. How simple is it? Quite simple, isn't it? Now you'd see that now I would remove this dog extends animal. Let's say the dog didn't have anything. Then you would see that the dog does not have anything called name in here. It has a toString, all the methods which it directly gets from object class, because any class in Java extends object. So even though I just said dog, it actually means dog extends object. Even here, I didn't extend anything, but in Java, everything extends object. So animal extends object. So that's simple, isn't it? Okay. Now let's get back to what we were discussing. So class dog. Now we didn't see anything called name. Now extends animal. Let's see if I get a name. There you go. So now I can access the value of the dog.name. Ideally, as I said earlier, there should have been a name should have been private. I should have a setter and getter, and then I should have called dog.set name and the name puppy. So this is basically what is called inheritance. Inheritance is a powerful, very, very, very powerful concept in an object-oriented programming language. Without inheritance, there is no object-oriented programming. So inheritance kind of forms the fundamental of object-oriented programming. As far as Java is concerned, you cannot extend two different classes. So I cannot create another class, let's say class dummy. And I cannot make dog extend animal and dummy together. Nope, that's not allowed. So in Java, you cannot extend multiple classes. Okay, there's a little bit of difference in opinion. I mean, you can extend multiple you can implement multiple interfaces, but for me, that's not really multiple inheritance. It's basically that you can implement multiple interfaces. Interfaces is completely different concept from inheritance, and I won't really want to combine those two together. So as far as Java is concerned, you can safely say there is no multiple inheritance, but it has the capability. A class can implement multiple interfaces, but that's different altogether. So now let's get back to whatever we were discussing. So we started off with inheritance. This is what is inheritance all about. What I can also do is, now what is allowed here is I can say animal is equal to new animal. That's allowed. I can create an animal. But if I don't want that to be allowed, so I don't want an animal to be created. I want really to make sure that I would know what type of an animal is there before I would allow that to be created. In that kind of situation, what we do is we make the thing abstract. So what we are saying here is I'm abstract. So as you can see right now at the bottom of your screen is a compilation error. So cannot instantiate type of animal because now animal is an abstract class. You cannot implement, you cannot create an instance of an abstract class. Abstract classes are also typically used in scenarios where you would want to extend that particular class. You don't want to create an instance of animal. But what I want to do is I would want to let other animals take the functionality from here. So let's say there is some cool functionality in here which other classes wants to make use of. And in those kind of situations, what I would do is I would make the animal class abstract so that the other classes which extend it get the functionality, but nobody would really be able to create an instance of the class animal, because animal, why would you want to create an animal? Animal is equal to new animal. No reason. So there you go. So that's our quick discussion on one of the good examples of you can look at ArrayList. ArrayList extends abstract. It implements multiple interfaces. It implements a lot of interfaces. Interface is another important concept. You can see that this particular class extends this particular abstract. So ArrayList extends abstract list. And if I look at abstract list, it has a definition of a lot of things. So for example, it has a definition for a method called add. And if I look at the array list, it's extending abstract list, and it also is defining the add. This is called overriding a method. So basically, what it's doing is it's overriding the method which is defined in this superclass. Abstract list is a superclass which is defining the add method. So array list is saying, hey, I don't really care about what the abstract list is defining. So take my definition. So whenever somebody calls add method, this is the thing which gets executed. One in the superclass is extended. But if the subclass does not define the method, then whatever it is in the superclass will be used. So let's and also you can see that there are a couple of things like an abstract method. So what abstract list is saying, I will not define how to get the element from the list. But what you should definitely do at a list is go ahead and define this method. So I'm saying it's abstract. So any non-abstract subclass of abstract list should define this particular method. So there you go. I mean, those are a couple of very good examples of inheritance which are directly implemented inside the Java itself. So you can look up a lot of other classes like sets, a lot of collection classes which would have similar relations. Let's now discuss about interfaces. Interfaces is not really an object-oriented concept, but I think interfaces is very, very fundamental to learning Java. So let's discuss what is interfaces quickly enough. Let's consider two classes. I'll consider class aeroplane, and there is another class called bird. Both of these, aeroplane can fly. So I can define a method fly in here. And even a bird can fly. Can I create a subclass class, some dummy with a fly method, and can we have it extends dummy and extends dummy? Is this a good thing to do? Inheritance is best used when there is a is-a relationship among the classes. In the previous inheritance example that we looked at, dog is an animal, cat is an animal, and therefore it made sense to use inheritance in there. But in this particular thing, whatever you want to come up with, I cannot say airplane is a flyable or airplane is a dummy, bird is a dummy. So in these kind of situations, inheritance is not the right thing to do, because actually these two things don't share anything except the common actions they can perform. So an airplane can fly, so airplane can do something, and similarly a bird can also do something. So the similarity is in the actions they can perform, but there is no similarity between an airplane and a bird. And that's the kind of scenarios where we go for an interface. Interface represents common actions. I mean, what are the common things that to access, common responsibilities you can think of? So if two classes share similar responsibilities, then probably we can create an interface. In that kind of situation, I create an interface flyable. And in an interface, you cannot have any definition of the thing. So you can only say this is the common responsibility between these two classes. And now I can say class implements flyable and implements flyable. When I implement a method, it should obviously be public. So I'll just make them public as well, just to get rid of the compilation errors. So now you see that we have created an interface flyable, and we have an airplane and a bird which extend that particular interface. Sorry, actually not extend, but implements that particular interface. And this is what is called implementing an interface. So basically, you go for an interface when it kind of represents the common actions, common responsibilities of two different classes. Java has a number of interfaces defined. List is an interface. So if you look at the interface of list, it defines all these methods. If you look at any of them, the body of the method would not be present. What would only be present is the signature of the method. So it says this is a boolean and it accepts some object. The name of the method is remove and it returns a boolean back, but it does not define what's in here. So what the body of the method is not defined in an interface. So the interface only gives the idea of what the responsibility is, and you would see a lot of other implementations of this list. So here the list interface defines a method called isEmpty. ArrayList implements list, and you would see that ArrayList also defines isEmpty method. So ArrayList is implementing the list and it defines the method isEmpty. And there are n other implementations of list that you can look up and look at how interfaces are used in Java. Now, let's quickly look at what polymorphism is all about. Polymorphism is another important concept in inheritance, and polymorphism is dependent on two different things in Java. One is inheritance and another one is an interface. So polymorphism really applies in those two conditions. So basically, let's quickly look at a quick example of polymorphism. In the earlier example, we defined an abstract class animal, and we saw that dog extends animal and cat extends animal. Let's define an abstract method in here. Let's say something abstract bark. Let's say abstract string bark. Now, once I defined it in here, then the dog class has to implement the method. So let's define that in the dog class. So dog, let's say, returns Bobo. Interesting, isn't it? Yeah. Okay. Anyway, and the cat, what does it say? Let's quickly say meow meow. Is that good? Does that make you happy? Okay, there we go. Now, what is polymorphism? I have two different classes, dog and cat, and we have another abstract class, animal. So what I do is I create an animal. So animal is equal to new dog. That's allowed because dog is a subclass of animal, and so a superclass variable can contain an instance, can refer to an instance of the subclass. So now I can say animal dot bark. What does it print? Let's add a sysout. If it was a real world project, I won't do a sysout. I should probably use some kind of logger, but let's take it easy and let's try and run this and see what's the output. Run as Java application. Bow. That's good. So it's printing bow. But you'd see that if I change this to cat, it prints meow. So basically the same code. So the same code prints different things based on what the content of the object is. So depending on what the animal is referring to, the output is different. The method which is called is different. And this is what is called polymorphism. Same code, different behavior. So when I have a dog object, then the animal.bark calls the bark on the dog. When I have a cat object in here, animal.bark would call the bark method in the cat. And this is what is called polymorphism. The polymorphism also works in the case of interfaces. So if we go and do it here, so if I say sysout here, say airplane is flying, and let's copy this over and say bird is flying. Now I can create an instance of flyable. So flyable, I'm an instance of type flyable, and it would contain an object of any of the implementations of flyable. So it can contain either an airplane or a bird. So airplane. So now if I do flyable dot, I need a main method. That's what is going on. So let me quickly create a main method. Okay, now I can do a flyable dot fly. So now you would see that based on whether I have an airplane here or a bird here, the fly method of the appropriate implementation of the interface is called. And this is the beauty of polymorphism. We really make a lot of use of polymorphism in real life examples. I mean, the entire concept of interface is based on this kind of polymorphism. Okay, let's now discuss about encapsulation. What is encapsulation? And let's try to understand it with an example. I have a scorer class. Let's just assume this guy is scoring a cricket match. So I'll call it cricket scorer to make it even more clear. In a cricket match, there are sixers, boundaries, singles, doubles, and all that kind of stuff. So what is encapsulation? Let's understand from the perspective of this scorer. So let's say I want to keep track of score in a cricket match. So if I was a primitive kind of a programmer, I would start off doing something like this. I would put a variable called score inside here, and let's say cricket scorer is equal to new scorer, new cricket scorer, and I can say scorer. Let's say there's a 1-run score. So initializing it. So I'll initialize it to 0. So I can say scorer.score. Let's say a batsman hits a boundary. So I'm saying scorer.score plus is equal to 4. So what is happening here is I'm directly changing the value of this particular thing without accessing any methods in here. And what happens because of this is that, let's say this class is not here, but actually somewhere down the line. Let's say there's a big project and this class is in one place and this class is in another place. What would happen if I change, let's say the programmer decides to change this int to a string, or he wants to store the score in a different way, then everything else gets affected. So this class has no control over this code now because everything else is dependent on it. So if this guy goes and changes the implementation of this particular class, you have to find out where all this particular guy is used and change everything else. Let's see how we could have implemented this in such a way that nobody gets affected. Let's also add in a few more methods. So let's say he scores a single in cricket is 1. So and he scores a 6 plus is equal to 6. And scorer, I want to print this score once in a while. So I'll say system, I'm not using a logger. I'll use a SOP. And I would want to print score. Scorer.score. So if we run the program, it would print 11 if I can add right. 11. That's good. So now, how can I make this more encapsulated? Encapsulation is basically making this variable more protected. So right now, the logic around score, the fact that when there's a boundary, 4 runs are added, this logic is in multiple places. So I don't want this kind of stuff to happen. So I would provide an alternate implementation. The first thing I would do is kind of make this private. So nobody would be able to change the variable value directly. So anybody who has to change the value of, wants to access the value of this particular thing, they need to do it through a getter or setter. So I'll quickly generate the getters and setters. Right click, generate getters and setters would be a way to do it. So let me just go ahead and do that. So now I have a getter and setter. So now at least everybody has to go through the method. So now I can say set score 4. Actually, it's not really true. We'll fix that very soon because it's not really set score, but it's more adding to the score. So I'll refactor and rename the method because I don't want to have anybody setting the score directly. So set score 6. And instead of doing this here, it should do scorer.get score. So now this is much better encapsulation. Let's rename. It's not actually set score, but actually it's add runs because we need to add the thing to the existing score. So this dot score plus score. Let's see if this program is working fine as it is right now. Okay, this is better. We can even make it better. For example, let's say batsman scores a 6. We need to add 6 runs. So he scores 3 times sixers and we give him 6 runs each. Let's say we want to encapsulate the fact that a sixer means actually adding 6 runs. We don't want to really put that outside the logic in here. So what I can do is actually create a method called public void 6. And when it's a 6, I want to add runs. How many runs do I want to add? 6. So now what I can do is I can, instead of saying add runs, I can say scorer.6. So the logic that a sixer means 6 runs is encapsulated within this scorer. So the programs which use this scorer, so this main program is using this scorer. There might be 10 other programs which are using this scorer. So they don't need to worry about how many runs a sixer means. They just need to say scorer.6. That's it. And this takes care of adding in the runs. So now I can call the same thing in here. And actually I can add other methods. So scorer.4. So to add in 4 runs. So now I can say scorer.4. This means 4 runs. Okay, good. Now nobody enough. Single. So this is called a single. So scorer.single. And for other kind of runs as well, you can add methods in here. So now I add in the appropriate methods, and now I can go ahead and run this program. And you'd see that this code doesn't change. And if I want to really make it even more encapsulated, I can even move the print logic in here. So public void print score. So I don't really want anybody else to directly access this code. So I can say in here, I don't need it. So I can say score. I didn't call the score method yet. So let's go ahead and say scorer dot print score. Run as application and score 23. The beauty of the whole thing, the whole change we brought in, is now this particular program, encapsulation example, knows nothing about the scorer. So it doesn't know anything about how the score is implemented. So whether it's an integer, whether it's anything. So now I can change this from int to long, or int. If I really want, I can store it in an array. Whatever changes I can make, I just need to make it inside the class. So if I change anything about the score variable, all the places which access the score variable are inside the class itself. And thereby, this is much better encapsulated than it was before. And this is one of the most important concepts in object-oriented programming in general, encapsulation. And once you understand encapsulation and once you start encapsulating your logic inside the class directly, it leads to much, much, much better object-oriented programming. The fundamental concept of object-oriented programming is encapsulation. It's all about having the data. Here, score is the data, and the methods that act on the data. 6, 4, add runs, print score. All these methods are encapsulated directly along with the data, and we create a blueprint, which is this cricket scorer. And that's really the beauty, and that's really the reason why object-oriented programming has really become famous. It's because of this concept of encapsulation, which allows data and the methods that act on the data are together. So it means whenever there's a change, the scope of the change is very, very limited. And if we design the systems properly, then we would have easily maintainable systems. Let's now discuss about coupling. What is coupling and how we can reduce coupling? Coupling is a measure of how much a particular class is dependent on other. That's the definition right here. It's basically a measure of how much a class is dependent on other. In an ideal world, there should be as minimum dependency between classes as possible. Let's consider an example. What we are doing in here is we are kind of calculating the cost of all the things which are there in a particular order. So an order, for the order we use a shopping cart. So what happens is on a website, a lot of people put stuff into the shopping cart and create one order. And at the end, we want to calculate price of the entire order, and to calculate the final price, you have things like tax, sales tax, a variety of taxes that add in, all that kind of thing. And we have a sample implementation. All the code is in GitHub. You can look at the repository in 28 minutes in github.com, and you should find these examples very easy. So this example, particular one, we have a shopping cart entry. So entry has price and quantity. So basically, I want to buy 5 brinjals. Each brinjal costs me 2 rupees or $2, based on wherever you live. A shopping cart consists of a number of shopping cart items. So, and the order consists of a number of a shopping cart and also the appropriate sales tax. This kind of a sales tax calculation might be very simplistic. The actual calculations might be more complex, but we are just taking a simple example. And the calculation of the total price of the order. So what it's doing in here, basically, this method, order total price, what it's doing is int I is equal to 0, I less than cards.item. So it's basically looping around the card and it's trying to sum up the price and quantity. So it's multiplying multiply price and quantity for each one of the items in the order, and it's trying to determine the order total price at the end by using the same steps. If you look at this particular class, this class order knows everything about the other classes as well. It knows that the items, for example, in here, it knows that items is an array. So if let's say I'm changing the items from an array, instead of an array, I'm saying I would want to change this array list. What would happen? Or a list. You can see that as soon as I change the list, there are compilation errors in the other class. So basically, the order class is tightly coupled to the shopping cart class. Let's undo the change. And it's also tightly coupled to the shopping cart entry class, because if I change, let's say instead of price, I want to call today's price or something of that. You'd see as soon as I change this, there are compilation errors in other classes too. And that means the order class is dependent on the shopping cart entry. So the objective of having minimal coupling is to have as less dependencies in classes as possible. How do we achieve that? Let's look at the solution to this particular thing right now. So let's build up the solution for this. If you look at this particular implementation of the same thing, in the shopping cart entry, we have a price and a quantity. So we have a get total price inside the shopping cart entry, which does price and quantity. So it's multiplying price into quantity and giving the total price. The cart contents, on the other hand, if you look at it, it's getting the total price now indirectly in here. So it's calling the item.getTotal price, which is defined above. It's using that method, it's looping around it, and it's calculating the total price and returning it back. And the order is only dependent on, it's calling the method get total price and then adding sales tax to it. That's it. It's not worried about anything else. Now, let's just say I'm changing this from an array to array list. Actually, I'm importing the list.ut and then it compares. The lucky fact was we are using an enhanced for loop, so it made things much easier. But even though if there were changes, let's say I'm changing it to a map or something of that kind, not really good, but let's say I'm changing it to a map. Even then, the only compilation errors you would see are inside this particular class alone. So the only thing which I need to modify is the cart contents class alone. I would not need to modify anything else outside this particular class. And the same way, if I'm changing this variable, let's say from price to price dummy or whatever, all that I need to do is changes in here. So this is what is also encapsulation, because the changes are encapsulated in here, as well as there is very minimal dependencies between the classes themselves. So a lot of these concepts that we are discussing, encapsulation, coupling, cohesion, are actually a lot tied up with each other. You can't separate each one of them and look at them individually. But actually, if you do a proper implementation, then you would end up with simple maintainable code just like this. So whatever we did here is try to reduce the coupling between different classes. It's always preferable to have as less coupling between classes as possible. Let's now discuss about cohesion. What is cohesion? Cohesion is basically a measure of how related the responsibilities of a class are. Okay, I was reading whatever is written here. So, what is cohesion? you have a class. Let's take this example: download and store. Oh, download and store. You already see it does a download and store. So basically, it's doing two different things. If you look at this particular class and what we want this application to do is it basically downloads something from internet. It needs to pass the data and then store that to the database. So basically, what we want to do is actually download something from the internet, kind of some XML or a HTML, parse it completely, and then store it to the database. So if you look at the current implementation, this is just a dummy implementation. But if you look at it right now, it's download from internet, parse data, store into method. All these methods are present in this particular class itself. And you have a do everything, which does download from internet, parse data, and store into database. So downloading from internet needs different set of utilities, different sets of classes, different set of dependencies compared to parsing it. So the fact that your the same class is doing all these three responsibilities is what this means. This class has very less cohesion. So it is downloading, it's parsing, it's storing into database, and a lot of other stuff. So it also needs to talk to the database to store into it, and a lot of other stuff. So this is an example of a low cohesive class. How does a high cohesive class look like? So let's take the same thing and let's look at the solution for that particular. The code again is in GitHub, so you can look it up. The ideal way to implement this would have been to have something like separate classes for each of the things. So I have an internet downloader class which downloads from the internet. I have a data parser class which parses data. I have a database storer class which stores into database. So the responsibility of the internet downloader class ends as soon as it downloads something from the internet. Ideally, the return type should be something. It should be some other class or something of that kind. But the responsibility of this class is to download things from the internet. The responsibility of this class is to parse the data. Whatever comes back from the internet, it doesn't matter where it comes from. The data parser, when it given some data, let's say it's parsed some string with content, it knows how to parse it and return something back. The database storer class knows how to store something into a database, given some data. So some data. I'm using string just because it's a class which is already available. So some data class, let's say, it knows how to store it to the database. And this particular class does not know the inner level details. All that it cares about is the high level process. So it knows, it takes care of, first I know I have to download, next parse, next store. So it just takes care of the high level method invocations, and it does not really do anything related to, and it does not do anything really related logic. This is an example of a better cohesive. So this example is, in this example, classes are more cohesive than in the earlier example. So cohesion is basically a measure of how different are the responsibilities of this particular class. This particular class has one responsibility, download from internet. So it's highly cohesive. This also highly cohesive. This is also highly cohesive. And if you have a good application, then you should have highly cohesive classes and you should have low coupling between them. So there you go. Those are some of the important object-oriented concepts that we discussed until now. Until now, we looked at all the important concepts in object-oriented programming like inheritance, interface, polymorphism, encapsulation, cohesion, and coupling. In this section, we would move to solid principles. Solid principles are kind of tricky thing to introduce at an earlier stage. I wasn't sure if I have to really put it as part of the course, but I thought it would be good to have an awareness about them. And that's the reason why I put it as part of this particular course. If you don't understand a particular section of this particular video, it's okay. That's not a problem at all. Solid principles are little difficult to understand. Even for an experienced programmer, I know of a lot of experienced programmers who don't understand them very well. That's okay. But the most important thing I feel is to at least get a knowledge about them, know that they exist, and know that there is some work there which is done on solid principles, and those are good principles to adhere to. So with that disclaimer, let's get started. You are creating an object-oriented program and you want to check whether you are doing a good job at it. If you adhere to at least a few of these solid principles, then you are doing a really good job at solving your problem using object-oriented programming. In my experience, I have found implementing solid principles difficult. Some of the times implementing them might make it much more complicated, but I always found it useful to understand them and have them at the back of my mind. And if I choose not to implement something according to a principle, then I would at least have a reason why, rather than not being aware of them. So let's get started with solid principles. The first one of the solid principles is something called a single responsibility principle. That basically means a class should have only one reason to change. Basically, the summary of this is anything should have one responsibility. I really extend this principle to a lot of things. Not just classes, but packages, and even further to a project, to anything. You should be able to give a one-line description of what it does. So when I ask, what does this class do? I should be able to give a one-line description of it. So similarly to a package, what does it contain? It contains all the data things, or at least it should be possible to give a one-line description of what it really means. That's kind of the thing which I take. Sometimes people really take it literally. If you try and define classes that have only one reason to change, then you end up with very, 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 very small changes, and probably very, very, very small classes, and probably that's not what you want. So take this single responsibility principle more at a logical level, kind of think as if you have to define, at least you should be able to define the responsibility of a class in one line. For example, the example which we looked at, I want to download the file, parse the file, and persist the data. And if you look at this particular task, it's doing multiple things. This class is downloading things, parsing the file, and persisting the data. So it's doing a lot of things. And another example is the example of an employee. So this class is is taking care of calculating the pay, reporting the hours, and also saving something. So this is doing a lot. So ideally, when I talk about single responsibilities principle for methods should be doing very related things. When I look at a method, it should be doing very, very similar things. The different methods in a class should be doing very, very similar things. It should not be that one method talks to the database and the other method is parsing something. Then this particular class has more responsibilities. Then we can split the whole thing into multiple classes. The next solid principle is open closed principle, OCP. What does that mean? It really means that anything that you create in software should be open for extension but closed for modification. Okay, complex, isn't it? What does it really mean? Let's look at an example. You can look at this area calculator class. It's basically calculating an area. You're giving a set of shapes to it, a rectangle, and you're looping around it, and you are adding the area and returning it back. When we started off, we started only calculating the area for one shape, which is rectangle. But at a later point in time, we expanded and we started doing more stuff. And what we started doing is actually calculating the areas for multiple shapes. And this is how the implementation changed. So what happened was, since the shape, we added in an if condition saying if shape is rectangle, do this, else do this. Compare this to the other implementation where actually we created an abstract class called shape, and rectangle is extending shape and it has its own implementation of area. And when there's a new shape, I would create a new circle as a shape. So I'm creating a new class circle as a shape, and it defines its own area method. And when I want to find the sum of areas of all the shapes, all that I need to do is loop around all the shapes and call the shape.area method. Compare this implementation with the earlier implementation of this particular thing. Whenever something changes, whenever there's a new shape, I have to modify this particular thing. So this particular thing is not closed for modification, because whenever there's a change, I have to keep modifying this. And whenever there's an extension, also I have to keep modifying this. So over here in this particular thing, if there is a new shape coming up, all that I need to do is create a new class extending shape and defining the area method. I don't need to really worry about changing the area calculation for all these things together. So I'm sure that whenever I make a change, I'm only changing for the new thing. I don't need to touch the existing code. Whereas in this particular example, in the example 1, I would have to change the implementation inside this particular thing, which would mean that there's a chance that I introduce a bug in existing code. So an open close principle is also one of the very important solid principles. Important solid principle is Liskov substitution principle. It says subtypes must be substitutable for their base types. Okay, very technical. What does it really mean? So whenever it defines the conditions under which you can use inheritance. A lot of people, whenever we want to reuse some functionality, we tend to use inheritance, and it introduces new complexities. Inheritance is not the silver bullet for reuse. That's the fundamental thing behind the Liskov substitution principle. You should decide whether there is appropriate situation for using the inheritance. So here, for example, I have a class rectangle, set width and set height, and I'm using that to define a class square. So what I'm doing is I'm doing a class square extends rectangle, and I'm doing a set width. I'm reusing the things width and height. So when I extend rectangle, I get the width and height. So whenever somebody does a set width, what I'm doing is I'm setting both width and height to that. Whenever somebody is doing a set height, I'm setting both height and width to that. So square does not have height and width. For the sake of reusing the functionality in the rectangle which is already there, if I make the square class extend a rectangle, then it would result in problems. For example, so somebody is writing a test like this. So he's doing a set width of 5 because a rectangle, right? So I should be able to do a set width, set height, and he's doing a 5 into 4 and expecting this to be the value. And let's say the value which is stored in the rectangle is in the instance which is stored in the rectangle is that of a square. In that case, this test would fail. So you should, basically what the Liskov substitution principle says is you should really use inheritance only when there is a right relationship and everything inside the base class applies to the class which is replacing it. There are attributes called width and height in rectangle which are not really applicable to the square. So in that particular kind of situation, you should not go and use inheritance. So just for the sake of reuse, don't go and use inheritance. That's basically the summary of the Liskov substitution principle. The next one is the interface segregation principle. Basically, what it means is any object-oriented programming has classes dependent on each other. Basically, the interface segregation principle says there should be as minimum dependency as possible between the classes, and those should be defined using the smallest possible interface. So basically what it means is there should not be one class defining a very big fat interface. A fat interface is something which has, let's say, 15-20 methods. And whenever I want to use that interface, whenever a class needs to implement this interface, then it has to define all the 15 methods which are there in this particular thing. Rather than that, it might be good if you have smaller interfaces, let's say interfaces of 5 methods each, 3 interfaces, 5 methods each, which would be applicable for, if I really want, I can implement 2 interfaces and then use those functionalities rather than implementing a very big interface. Let's take this example on interface segregation. There's an animal and there's a feed method in the animal, and we have a dog and tiger which implement those methods. So this is how the code was at the start. Later, there was a groom method which was introduced. And the groom method usually is only applicable to domestic animals. But just to make reuse of the existing functionality, what we did was added the void groom method, and dog extends animal and void groom. I mean, you groom a dog, but tiger, do you want to really groom? I mean, that's basically a dummy implementation just to keep the compiler happy, because now tiger also extends animal, but if you don't implement the groom, then compiler would start complaining. So you give a dummy implementation. This is an example of a place where I'm not really implementing the interface segregation properly. A better solution would have been to have pet extends animal and let the pet have void groom, and let the dog extend pet. Tiger keeps extending the animal. Now tiger doesn't need to give a dummy implementation just because some other thing had an extra method. So the most important thing is you should only have methods which are applicable to you. I mean, if you keep bulging up classes with dummy implementation, it results in very bad maintainability. The last one is the dependency inversion principle that basically says depend upon abstractions. That basically means use interfaces as much as possible rather than using concrete classes. So, for example, this is one implementation of the copy method where we are actually trying to read something from one device and put it to the other device. So basically, we want to check whether the device is printer or the disk. So based on whatever it is, whatever is entered on the keyboard should either go to the printer or the disk. This is one implementation. Compare this with the other implementation. So we have an interface reader, interface writer, and when we want to copy from a reader to writer, all that we do is something of this kind. So this is much cleaner implementation compared to the earlier example one, because this is in here, whenever there's a new device added in, you need to change everything in here. But with this kind of an implementation, you can add in as many readers as you want, add in as many writers as you want, but you don't need to really touch the copy method. The copy method remains as it is. All that the readers and writers need to do is implement the appropriate read or the write methods. So this is basically the dependency inversion principle, where you actually try and depend on a lot of interfaces, try and depend on a lot of abstract stuff. So try and depend on abstractions rather than concrete stuff as much as possible. What I found in my experience is that when we try object-oriented programming for the first time, we don't really get it right. But it's basically a learning experience. Over a period of time, when I start with trying to implement object-oriented programming, what I found is either I do very less object orientation or I end up overdoing the object orientation. And the proper use of object orientation is somewhere in between. And finding that is very tough. So all that we can do is keep trying to improve ourselves, keep trying to learn, and good luck. Until we see you next